we come to the second part of the lectures on stay cables, where we deal with the third of the three important, and in itself maybe today the most important type of stay cable, that's parallel strand cable. And then we will go a little bit into the anchorages of stay cables in general, tower and beam. And we'll talk a little bit about the sizing, how we calculate the diameter of these stay cables. Now, I showed you important today are lock coil rope, parallel wire, and now parallel strand cables. The basic idea from the parallel wire cables, having those tension members in parallel and not losing through the twist, strength and stiffness, is also true for the strand cables, and they were the later development because people said, oh, that's a good idea to have it parallel, not twisted. But strands, because the individual wires, 5 milli wires of strands, are the smallest there are, they are even stronger than the parallel wires. 1872, it's in development to 1770 or something like that. So again, for the same 1 ton weight, I need less steel. Money talks. That was the basic idea, and the initial was also done in our office for the Olympic roof in Munich. And if you think of that, there are very thick edge cables and so on. We were the engineers for the Olympic roof at that time. And there was used parallel strand cables practically for the first time, but with a high M anchorage. Rather special, but it worked very well, so that was the beginning. And later people said, we want to do it on site, then we can't cast it. So they then said, okay, we'll use, like for the strand tendons again, wires we use BBR button heading, strands we use these little wedges, like done for stranded. And that's how the development of the parallel strand cables started, from the parallel wire to the parallel strand. The advantages are that the parallel strands, very roughly speaking, are fabricated on site from the individual elements. The strands are delivered, the PE pipes are delivered, the anchorages are delivered, and from these pieces it's put together. So we don't have to transport large weights. Then we can stress individual strands with small equipment. We see all that in the lecture cable installation later. Of course, and then the very important thing, because we build them up from individual strands, we can also exchange individual strands. So if things go wrong, we not always have to exchange the full cable, as for the others, but we can exchange individual ones. That is, of course, the winning is it's more economic than the others, of course. Okay, it has no predetermined lengths and so on. Now, how do these parallel strand systems look? This is a typical DSI system. All the major fabricators in the world produce parallel strand cables. I hope I don't forget anyone. BBR in Switzerland, VSL in Switzerland, Freyssinet in France, Shinko in Japan, Cable Tech in South Korea. I hope I had most of them. And they are also fabricated in China. I've been to places, but I don't know the company. So whenever I show here Freyssinet or VSL or DSI, they all sent me their slides. So that's where I got them from. I know all these people. Or Shinko. I'm not favoring one or the other, to make that clear. They are basically equal. But they have different developments. So this is a typical situation. We have here the parallel strands coming in. They are here spreading out to be able to anchor. Then we have a steel anchor plate, and at the end there are wedges. And then we can support them here on these bearing plates, for example. They all basically look the same, like this. Cross-section, we have the parallel strands. Now each strands, the modern type of what we are talking is so-called monostrand. All the strands consist of 7 wires. Now we use today only the 0.6-inch diameter, 15 millimeters, with 150 square millimeters, which is a little bit thicker than the older one. And so these are the individual strands, and the wires are galvanized. The interstices are filled with what we call here grease, and then they are, again, development, I guess, surrounded by a directly extruded PE pipe. So every single so-called monostrand is a unit in itself with corrosion protection. I repeat, the wires are galvanized, number 1. There's grease in between the interstices, number 2. And there's a PE pipe around. So we have 3 barriers around every individual monostrand. They are then placed together, and there's an additional PE pipe. This is here shown 2 half pipes which can be snapped together. There's a locking mechanism here. So if you want to, that's a 4th barrier we have here. Now these anchoring, we see here a monostrand. Here at the end are the 7 wires, galvanized, greased, and a PE pipe directly extruded, PE sheath, I better say. It's not a pipe, but it's directly extruded. And then we have these wedges with which we clamp the wires at the end. First of all, initially, these PE coating was scraped off, and in order to have the clamps acting directly on the metal. But with the development, it's not necessary anymore, because of course that's expensive. You had to heat it, and well, all sorts of things. Then the next big question is, if you start with a wedge, with a regular tooth pattern, same teeth at the beginning and at the end, and you make a fatigue test, it breaks rather early. Why? Because the force goes, most of it, into the first 1, 2, 3 teeth, because they bite, and there's very little force transition in the end. So the length of the wedges is not active, but everything happens in the beginning. And that sudden change of stress means little fatigue. So the development was that the teeth were non-uniform. Little teeth at the beginning, increasing over the length. Big teeth at the end. So there was a uniform load introduction because of the difference in teeth over the length. And that's also developed today, that the fatigue strength is little, very little. I'm not saying not. but very little influenced by the wedges. That's a big development here. You may remember from the first plate, the permissible fatigue range for parallel wire and parallel strand cables is the same with 200 Newton per square millimeter. It's a little bit advantageous for the strands, but okay, we can live with it. Now the corrosion protection I have already basically mentioned. We have the hot dip galvanizing with all sorts of details you don't want to know now, how many gram per square millimeters and all that. It's all in the script. Then we have the wax filling in the interstices, and we have the directly extruded high density PE. That's what high density polyethylene. That's what the HDPE means. In addition, we have a PE pipe around. The picture is not very good, I'm afraid. No, you can't see. No, it's all black. I must use a better one. But basically, we have the internal, say, 6, 7, 8 millimeters mechanical strength. Then there is an outer coloring area. And today, we have helices, helices, I think it's a plural, around, like the Scruton helix you may have heard, against rain, wind induced vibrations. You'll hear about that in a later lecture. And the thickness is not necessarily, or the thickness for the parallel strand PE pipes the thickness is less than for the grouted PE pipes of the parallel wire, because there is no grout. The space between the monostrands and the PE pipe is not filled with grout. It's not necessary. The monostrands themselves are sufficiently corrosion resistant, and it's more a mechanical and aesthetic surrounding the PE pipe. Then we have the coloring problem I mentioned to you, and there have been many, many tests how you can UV resistance and the color stability, and there are a multitude of tests. They quote here 90 years in the south of France, so I'm sure it's a Freycinet slide I have here. The others have the same, and you can always also make it a little bit metallic looking if somebody wants it. These are pictures of installed parallel strand cables. We see here these helices. Here we have them in red, here we have them in white, and here we have them in yellow. You can choose most any color you want today as a client. There is a new development in corrosion protection, which I like to mention. It so happens this is now VSL, Swiss fabricator. VSL meaning Vorspannsystem Losinger. That's VSL, one of the major fabricators. And they have come up with the idea to protect the steel wires inside by dry air. The concept is probably familiar to you since many years, at least 20 years. The inner part of steel boxes is only painted once in shop, and then there is a dry air producing unit inside which dries the air, circulates it. So the humidity is, well, they say here 60%, others say rather 50% as a maximum, but under this dried air, no corrosion takes place. And it's a proven system for, as I say, steel boxes. You have, of course, to have them airtight and have entrances which you can bolt airtight together again and all that. So it's well known. And now they say, why can't we do it with cables? And again, they are not really the first ones. It was first tried, to the best of my knowledge, for the Forth suspension bridge in Scotland. You may remember the Forth railway bridge, a large truss, 400-meter spans and so on. Close in the vicinity of that old Forth railway bridge is the Forth road bridge, 1,016 meters, longest suspension bridge in Europe, I think in the 60s and so on. I've worked on an alternate for that. I've been there several times. And the problem with the Forth road bridge is the corrosion of the wires of the main cables. So they've tried all sorts of things, but now they have tendered and even awarded the construction of a new bridge, a cable-stayed bridge, which I have shown to you, Forth Bridge, where we have a series, 3 main spans and overlapping stay cables in the center, if you recall. Anyway, the last try to slow down the corrosion of the wires was to have a new surrounding. It was, I think, a wrapping, to make it airtight, and then blow dry air through the length of the wires. And apparently that worked very well. And the corrosion protection seems to be stopped. So there's another major suspension bridge in Japan where from the very beginning they used this system. They used, I say very roughly, a big PE pipe. You know, these main cables of suspension bridges, they are, say, easily 60, 80 centimeters diameter. It's not. You have a big PE pipe, blow dry air through it. That's it, corrosion protection. And so I think from this origin, VSL said, well, why can't we do it with stay cables? And they basically do it this way. They have a dry air unit at the tower, and they have then, we have the PE pipes around the strands, which are not grouted or so. It's free, it's air in. So they can circulate the air there. And now take it one step further, which I think is really interesting. It's not yet done, but I think it's a good idea. You can then say, now we combine the dry air in the beam, steel box girder, and the stay cables, and we use a closed system, use the stay cables for air transportation into the beam, and take it out or blow from both sides and so on. So that would be a closed system, stay cables and inside of box girder with corrosion protection by dry air. It's a new interesting system. Maybe it works. Practice has to show. Now, the fabrication of these parallel strand cables, one of their big advantages is that they are fabricated on-site from their individual components. And we will see in detail in a later lecture on cable installation how that goes in detail, but suffice it to say we have here delivered the strands on reels individually, and then we have here a pull wire to which we connect with the so-called shuttle, the strand, and then this pull wire pulls the strand up, and it's anchored individually, stressed individually, one after another, until the cable is filled, completed, and theoretically later on, if by magnetic induction, as I showed you, we see there are strand breaks we could exchange individual strands. Now, very briefly, tests on fatigue strength. The same for all types of stay cables. This is taken from the PTI test. PTI is in the US, Post-Tensioning Institute, and we made in the 80s the first international code on stay cables. And at that time there was always only DIN, what was it, 18,800 with locked coil ropes, but that was only valid for Germany. Nobody used it outside Germany. And so it so happened I was a member of the code committee, and we made the first codes for parallel strand and parallel wire cables, and these have been taken over by all the FIB and other codes. Now, basically, fatigue tests function this way. We have a big testing machine with hydraulic jacks pulling the cable, and we use 2 million cycles, which is the Wöhler strength. There's also 2 times 10 to the power of 6. There's also what we call in German, Wöhler is Dauerfestigkeit, Wöhler strength, fatigue strength. And then there is Betriebsfestigkeit, which I call endurance strength, which is 10 to the power of 8, 100 million cycles. But here we use the abbreviated 2 million cycle test, and the cable is stressed to the permissible stress under service conditions, which is 0.45 of GUTS. Now, you all have GUTS, I know, but this means guaranteed ultimate tensile strength. GUTS is the American word. And the stress range is 200 megapascal, and so it's cycled this way. And after the 2 million, the cable is pulled until it breaks, and then it has to reach at least 95% of GUTS. You could say, why the hell, I mean, we want 100%. Yes, that's nice, but a little loss there is from the fatigue. So we've, at that time, I know it was, in the 80s, 30 years ago, we've decided 95% will be good enough. So that's a requirement basically from all codes, and all new cables have to undergo, for example, this fatigue test and prove they have the fatigue strength. There are all sorts of tricks. Well, I will just mention one. You have to watch the contractors or fabricators. You won't believe it. They found out, there are different strands have a certain variation in strength. Some strands are a little bit less than 100%, individual ones. Some have a little bit more. And so what they did, they selected by diameter for the test cables only strands with a plus strength. So they started up already, say, with a GUTS of 105%, because they pre-selected the strands and did not take the usual. And then, of course, it was easy to come out with this. We found ways to take that out. I just tell you, you can't imagine the imagination of contractors to get around your test requirements. Just remember. Okay. No harm done. It's a little war of thinking. One thinks up and the other thinks how he can do something against it. Also, we try to check the water tightness of these monostrands. What we do is a 1 meter head of water, pressure on, and then it's for some weeks and what have you. And this must not happen. There must no water drip out. And there's also a CIP test. There are FIP codes, the PTI code, of course, all sorts of things. And there you test a fully assembled cable over, and then it's heated water, and you have a transverse check to have the anchor head a little bit bent, meaning what happens to it from wind transversely or things like that. And then again, for its getting different stresses between 0.5 and 0.2 guts and all sorts of things. And again, it must not leak. So then there are all tests for the PE pipes. You know that first of all, after sun radiation, the yield strengths I showed you must not decrease because of the 2% soot. It does not. And you can then check the color intensity after exposure to UV. There are all sorts of tests. Now, finally, valid for all types of cables, of course. Once the stay cables are built in, we have to monitor them. We must make sure nothing happens to them because, so to say, the well-being of the bridge depends that the stay cables work as they should. Okay. One thing which we can do is we can place an accelerometer on stay cable, which measures the accelerations, not the velocity, but the acceleration which a cable exerts when it vibrates. And by these accelerations, they are directly, of course, connected with the amplitude. We can find out with how many amplitudes a cable vibrates due to the various reasons. We'll have a special lecture on that. And of course, from the decline of the oscillations, we can then assess the actual damping due to whatever reasons. So we can measure that. And then, of course, this is a write-up if we have, due to what reason ever, wind or some heavy truck running there, and things like that. We start with vibrations, and then we have to find out that they decay rather quickly and do not go on and do not increase. Then we have to do something. We'll see about that later. Then we can permanently, directly measure the force in the cable by installing a load cell, we call it, which is basically a hydraulic jack, into the cable anchorage. We use one strand anchored here together with the others, and then the gauge reading of this of this load cell, we call it, because you don't stress, but you just measure basically the hydraulic pressure. And then we can permanently record the force. There can be changes in force due to shrinkage and creep, or breaks somewhere, or change of support conditions if a bearing goes, all sorts of possibilities. So we just check the force stays the way it should. And together with other things, on a permanent basis, we can measure them here. It's all here listed what one can measure, and then it all runs together in a control office, and it's all noted down. I've seen it or been involved with this monitoring of stay cables for bridges, and my experience, it is an extremely dull business. Nothing ever happens. Thank God for that, but I have never seen anything. So it's well meant, and normally the client who doesn't understand the thing says, we want to check it. It's okay, we can do it, but nothing happens, and if there is a problem with the cable vibrations, you see that without monitoring, and then you do something about it. And to check the inner corrosion, I showed you the magnetic induction, which you do all 2, 3, I don't know, years, and all that. But this permanent monitoring, extremely dull. I say, when I was involved, nothing ever happened. So it's a little bit a waste of money, and it saves for clients who are unsure and say, let's check it. It's okay, we can do it. Now, cable anchorages. Whatever type of cables, I always leave out the parallel bar. They are special, they are cast in. But we use the block coil, the parallel wire, and parallel strand. Again, those are the three which are of interest. And they all have basically similar, say, circular anchor heads. Inside they may be conical or whatever, but at the outside they are just something depends on. They can be very big and very heavy for the cables. Now, very generally, how do we anchor stay cables? In details, we see that with the examples of different bridges we come to in the next semester. I just make it very roughly. Well, if we have a concrete tower head, the general solution is that we have a box cross section. We anchor the stay cables here and tie them together with post-tensioning. That can be done more sophisticated, I'll show you later. If we have a steel tower head, we anchor the stay cables between some longitudinal, some or more, 2 or more plates, and then we just have to shift the force over crossbars here into the plates. That's the basic idea. At the beam, in concrete, the classical anchorage used for most concrete cable stay bridges. I would have to think about something where it's different. We cast in a steel pipe, and the steel pipe is thick enough to have the anchor head passing through, and then we fix the anchor head in some ways. We come to here underneath, and that's it. So, and we use here a centralizer, an elastomeric washer, and we use some sort of neoprene boot to close it against rain, weather, and so on. That's more or less what everybody does. Steel normally can be used various ways to transfer the cable force into the web of the beam. Most direct anchorage is if we make a web extension, if we extend the web through the concrete or orthotropic deck, and into this extension we weld again a steel pipe and then anchor the stay cable the same way at the end of the steel pipe as here. That is the most direct force introduction from the stay cable into the web where it belongs. Normally it's done beside the web, and then we have some eccentricity moment and transfer can be done. But this is the most interesting. Was first done for the Annecis Bridge in Canada, in British Columbia, from my friends Peter Buckland and Peter Taylor. The problem, of course, is the force transfer here. You can't weld it on top of the top flange. Then you have tension across the plate, and you get lamellar tearing maybe through thickness. Tension is much smaller than transverse. What you do is you make a pocket, you cut a slot into the top flange here, like this, cut a slot, stick the new plate through, and then make a butt weld here. And this butt weld has the same strength, fatigue strength and so on, than the rest. So that's a little detail, of course, you have to take into account. Now, how this was the anchorage basically of the stay cables to tower and beam, so to say, overall. Now, how do we prevent the anchor head from slipping through? I want to go in some detail. There we have to look into the different types of anchor head shapes. Here we have what I mentioned more and more, the typical cylinder anchor head. Now that's for concrete or steel pulled through a steel pipe. And then we place here some washers underneath the anchor head, Scheiben, Unterlegscheiben, then washers. Even split washers, Halbscheiben, which we can then put in. They have an inner opening which goes just around the cable, and they are wide enough to bridge the distance between the anchor head diameter and the inside here of the steel pipe. So they are placed here and they are resting on a base plate, and you can all calculate that. But that's what basically prevents the anchor heads from slipping through where they came from. Another possibility is to use cylindrical anchor heads with an outside thread onto which we can screw a support nut. And then we have the system here. We have the stay cable. That's where the cable is. And we have the pressure plate. And that's the anchor head which came through here. And then we have this support nut screwed on, and it rests then on the base of the support nut. And by changing, if we pull at the check, pull it longer, then we can more screw on the support nut. That means the cable length is defined by the position of the support nut in practice. Here, the cable length is defined by the thickness of the washers. I remember for a cable-stayed bridge early on, Pesco Kennewick, we had the construction manual, and there we stated at this and that stage you must have a shim thickness of, say, at that time 3 inches, and then you reduce it to 2 inches and so on. Shim thickness or position of support nut defines the cable length after installation. The open sockets I just mentioned for completeness, it's only for smaller bridges. There we have a pin normally at the end, and we change length by having this sleeve with an internal thread to use that. You use it for sailboats, for smaller things. Huh? Now, I wanted to have a word on the cable anchorage at towers, because that is more varied than at the beam. At the beam it's normally always the same. I start with the more unusual, and that is that we anchor the stay cables at the tower not separately, as we normally do, but we have them continuous, running through from beam through the tower again to the beam. An advantage can be that you save the 2 cable anchorages at the top by going through continuously. It's always cost which is behind these crazy ideas. Jean Muller did it for the first time here. The problem, of course, is you need a saddle, and the fatigue strength of the saddle was always a little bit subject to discussion, and therefore it wasn't normally used. But if you use a central cable plane, of course with a box girder, then the space you need for the tower, so to say, is wasted over the length of the bridge. You have here the full width, but needed only here. So you want to have the tower as slender as possible. Yes, I know you can taper out at the top. There are all sorts of ways. But if you don't want to do that, then you want a slender tower as possible. And the most slender cable anchorage you can get, if you just have the cable run through, no anchor heads and things like that. That's how that came about. And of course, then it came into the codes, FIP and CIP and so on. And I don't have that old one in the one slide I was thinking. Now, if you have a life load in the main span, then the cable forces, I'll show it to you here. If we have a track load standing here, then the cable force is transferred, the force is transferred by the cable up here, and a large part of it goes up then to the backstay cable into here. Which means this part of the cable is under life load stress, and this basically has no life load stress, roughly speaking. Okay, so we have a difference between left and right in the cable, up to 30-40% of the cable capacity. And that the cable must not slip through, must not slide. So how to take up the cable difference, the force difference between main span and force span. Basic problem of the saddle. What is normally the traditional method from suspension bridges is that we use curved plates with grooves into which the wire, the cable is placed into a groove on top, little distance, and then we have bolts, and we strengthen, clamp it together. And then by friction, we can have a life load force in here, and no life load in here, and the difference is taken by friction. Okay, so far so good. What about the fatigue strength now in this clamped cable? With suspension bridges we were not interested. There's a different situation, but with the stay cables. Well, there were first initial tests made, and they failed, and no good, and we were thinking about it. Finally, by making the ends curved, that there is a gradient force increase in the saddle and all sorts of tricks. People succeeded in getting the fatigue strength also for saddles, okay? And there's one, again, from VSL, a new development for a saddle. The strands run through, and they have a special cement mortar with which they fill this part here. The PE pipe is taken off, so the cement grout, I call it, can touch directly the wires. So it's cast in, plus there are transverse plates which are V-shaped, and the individual strands run through, and by the force which is in there, they are pressed down and clamped into these V-shaped openings. So cast in plus friction in the V-grooves. That together gives up to 70%, they say, of life load forces, plus same fatigue range. Well, they have the tests. So that's the latest in saddles, but it is a little rare. Normally, we anchor the stay cables individually at the tower head. A disadvantage, of course, of a saddle of a continuous cable is if you have to exchange the cable on one side, theoretically, you can't do. You have to exchange the full cable. Now, normally, we don't want to bend and the fatigue problems of what we want straight cables, anchored top and bottom. So then there is the current development since, 10, 15 years is to use what I like to, first of all, we use concrete towers, mostly. because it's cheaper to carry a compression force in concrete than in steel, period. Now, how to anchor in concrete? And the latest development is to use what I like to call a composite anchorage, where we anchor the cables proper in a steel part and use the steel part to transverse the horizontal components directly through here. The vertical component is then introduced via shear studs or so into the concrete. So further down we have compression in the concrete, but we take the tension between the forestay and backstay in this steel tie. That's a picture, and that is, I'm sorry there is no person, but the person would more or less fit underneath here, the steel part for the Normandy Bridge. We will see that all in detail. We have a full lecture on Normandy later. And so we had the saddles, we had the composite anchorage, and now we come to the classical concrete anchorage. When we have a single or twin, this is a example from, this is Baytown. We also used it for the Helgeland Bridge, first for the Baytown Bridge. If we have a concrete box and we have the cables here, we have to carry the horizontal components through. And this is for the material concrete. The appropriate solution is to post-tension it. And if we think about it, then, and we use then what we call a strut and tie model, Fachwerkmodell. We use strut, compression member, tie, tensile, tension member, strut and tie model. You can say, okay, I use overlapping loops like this and like this. And the force transfer, classical strut and tie model, we can think of the following. 1/2 of the forces goes in direct compression into the end anchorages of the tendons. It cannot, so to say, slide off. The concrete cannot go away because we have here end anchors of the tendons. And the other half from the other tendon, where we then have the loop, goes by radial forces like this. The second half is balanced by radial forces from here. So a classical strut and tie model to show how to do appropriate for the material concrete to anchor it. Well, that's all very beautiful, and I've done it twice for Helgeland and Baytown Bridge, and it's very nice. However, contractors say, well, that's all very tedious, and it is short tendons. I mean, this was 12 meters. Okay, we made it double, but it's short tendons and so on. Although it's a very good system, it's not much used today. It's used the steel part, cast in, and don't fiddle around with the tendons. That's how the practical use sometimes overcomes the good theoretical solution. Now, cable sizing. I do that very briefly. Cable sizing, especially in Germany, since it has fallen into the hands of more theoretically working people, has become very complicated. I had my friend Rainer Saul writing it out, and it's, I think, 10 pages in the script. I've just translated it into English the other day, and I thought, hell, that's really complicated. Now, I will just give you the summary. If you're interested, you can read all that, but for here it's too complicated. It's the combination of transverse bending with this and that, and not nice. Now, basically, we have two ways of sizing stay cables. Traditionally, it was done for service loads with permissible stresses. And there, what you like to know is the permissible stress for main loads, meaning dead load and live load. It still says beta N, we have to change that into GATS. 42% of the ultimate strength for lock coil ropes and 45% of the ultimate strength for parallel wire and strand. And that's basically all you need to size stay cables, basically, as far as I'm concerned. In addition, you like to know the fatigue range. Permissible fatigue range for lock coil ropes is 150, parallel wire and strands is 200. The test conditions and all that find somewhere else. And if you exchange a cable, you remember Kühlbrand bridge. Cables were deteriorated, they had to be exchanged, and if it's planned, you can allow a little bit higher stress, 0.5 instead of 0.42 and 0.63 instead of 0.45. That's, as far as I'm concerned, basically what you need to know. That's mainly the way I've sized stay cables all over the world. Now, of course, nowadays we normally size things in the ultimate limit state. That means instead of permissible stresses, we have load factors. And the load factor against tensile strength, against ultimate strength, is 1.65 and 1.54. The lock coil ropes are always a little more suspicious because they don't have the fixed yield point. They have these little changes. It's all outlined in the script why the lock coil strands are permitted less load than the parallel. That's here the same. They have higher load factors or smaller permissible stresses here. And now, against 0.2 yield, the wisdom of our betters has decided it should be a safety factor of 1.1 for both. I just tell you. So that's, I think, all you need to know about sizing. If you have to do it, I'm afraid, read the script, 10 pages. It will enlighten you on the difficulties one can think of. Well, I don't have to add much to the summary of the last lecture. We have now extended our knowledge to the parallel strands. They are used overwhelmingly all over the world because they are most economic and they can be done in pieces. We will see that big advantage in one of the next lectures on cable installation. Thank you very much.